Hello, welcome to your Tuesday lesson. Hope that you're enjoying the pump up music. This is what I'm listening to because I'm an old lady and I love his whole look and vibe. Amazing pink satin jackets, crazy mustache. Anyway, back to the math. Okay. So this is a big review lesson. This would be a good lesson to take out a piece of paper and a pencil, follow along with notes that you can look at on Thursday when you have your quiz. We can't wait to see your quiz. We've been working so hard and we've covered so much, evaluating logs, looking for this missing exponent, using log laws to expand and condense. These are all the essential questions that now we can answer with all of our hard work. We've used product, quotient, and power laws to condense and expand logs, and we know what we're looking for when we evaluate a log. For product, quotient, and power law, we know how to recognize which one we are going to use. For product, we see that there's multiplication in the parentheses. For quotient, there's division. For power law, we have an exponent on top of our argument here, the x. And we know how to expand these. For product law, we're popping it out with addition. For quotient law, we're using subtraction. For power law, we're bringing that exponent down in front. Easy peasy. You'll see power law highlighted today for how useful it is. It is super, super useful with logarithms, finding missing variables. It's really cool. Okay, so what are we looking for when we evaluate a log? That was like last week, like when we were converting logarithms into exponential form and we're looking for that missing exponent. We were saying, okay, log base 6 of 36 equals x. 6 to the what equals 36. We looked at our power table or we knew it in our head. X equals 2. 6 squared equals 36. Sometimes it's really easy to find that missing exponent. And sometimes, like in today's example, you'll see that it's really hard. And so logs are really useful. Today's essential question, how can we use logs and the laws of logs to solve for values, IRL, or in real life? And how can we isolate a variable in logarithmic equations? You'll see that we can use logs, like we can subtract, divide, multiply them, just like any other value in an equation to get our variable alone. And what is this change of base law? Our example, IRL in real life, we're looking for time. How much time will it take me to accrue double my money if I invest $600 at an interest rate of 12% compounded monthly? Here's our routine formula for exponential growth of money, where A is the total that we're going to get, P is the principal, what we're putting in. You might already start recognizing what is our A, what is our P? Well, P is going to be 600. That's what we're putting in to start. And if we want to double our money at the end, that's going to be 1,200 or 600 times 2. Let's start filling in the other pieces. R is the interest rate. They told us that our interest rate is 12%. So that will be 0.12 here on top. N is how frequently it's compounded. If it's compounded monthly, we're looking at the year as a whole for compounding. There's 12 months in a year, so that means we're putting this over 12. The other piece that we're filling in is this NT. I think typically you're used to seeing this just to the time, but this is a more accurate formula for the exponential growth of money to the NT. Okay, so this is our problem. This is our problem where you're going to see that logs are super useful. We have our variable in the exponent. We can start cleaning it up just like normal. Let's start cleaning it up and using inverse operations to get our loan. I can divide the 600 right away. I can clean up inside of these parentheses. 0.12 divided by 12 is going to be 0.01 plus 1. Perfect. Now we have something that looks more familiar. It's already in exponential form, but it's not really clear. Sometimes it's easy to see what is the exponent that I need to raise a base to in order to get the number, but this we can't do in our head. There's no power table for base 1.01, and anyway, we wouldn't be able to carry one out. It's just so super hard to do this in the way that we're familiar with. So this is where logs come in. We can take the log of both sides. We're using log base 10 because this is the log that's in your calculator. And now that we take the log of both sides, we can use log laws. So we can take this exponent, we can bring it down to earth so that we can start isolating it. So we're putting it in front. Now that we put it in front, we can start isolating it. It's being multiplied by this whole expression here, log base 10, 1.01. So let's divide by that on both sides. And then you just put this into your calculator piece by piece. First the numerator and then the denominator. If I take log 2, that gives me 0.301. If I take the log of 1.01, I get 0.004. And if I divide those values, 0.301 divided by 0.004, I get 75.25. Easy. Last step to get t alone is to divide by 12 on both sides. And just like that, logs helped us get our answer. It would have been nearly impossible to do without them. It'll take us 6.27 years to double our money at this amazing rate of 12% compounded monthly. This is a good savings account. If you see one like this, jump on it. So our essential questions today: how can we use these log laws and logarithms to solve for values in real life? We just did it. We found out how much time it would take to double our money. And we couldn't have done it without taking the log of both sides. This was a critical step because it allowed us to use these log laws to manipulate the expression so we can start to isolate our variable. It would have been just super hard to solve for it when our variable was here in the exponent being multiplied by 12. What? No way. How can I isolate the variable in an equation with logs? You can treat the logs like anything else and divide by them, multiply them, and most importantly, taking this log of both sides allowed us to use the log laws. This was really the critical step. So your quiz on Thursday won't have word problems like that. Just wanted to give you an example in real life. It'll be a lot clearer what it is that we're asking you to do. You won't have to do so many steps. But you are going to see your log laws. You are going to condense and expand logs. You are going to evaluate a couple logs. So like last week's work, where you're using the power tables, and you're going to have one more thing, which is this change of base law. This is really easy. It's going to take probably 60 seconds for me to show you. So any logarithm, like log base a of x, you can solve it by expanding it into this version. You are making this log base 10, and then you put the argument over our old base. So here's an example with real numbers. Log base 6 of 1/3. You can solve for that this way. You don't have to look at a power table. This is a really powerful way to evaluate this log. What is the exponent that I have to raise 6 to get 1/3? It's not that obvious. It'd be hard to find that on a power table. So change the base, log base 10, log base 10. Put your argument on top, base on the bottom, and then evaluate it one at a time. So put it into the calculator, simplify this log base 10 1/3, simplify this log base 10 of 6, and then divide.